I wanted to work through a homework problem here that when I worked through occurred to me that would not be maybe immediately obvious how to solve, but when you read the textbook, it is actually pretty insightful. So first of all, I want to remind you that if you click here, question help, go to textbook, the textbook will open in a pop-up window. And if you're having any trouble with pop-up windows, make sure your pop-up blockers are turned off. And if you don't know how to do that, ask Google or ask me. I can help you figure it out. Google can also help you figure it out. So let's go ahead and look through the text here because I'm not sure how to figure out what's going on with this problem. Suppose you just received a shipment of 15 televisions. 3 of the televisions are defective. If 2 televisions are randomly selected, compute the probability that both televisions work. What is the probability that at least one of the 2 televisions does not work? Now, I don't know about you. When I read that at first, I felt just a bit overwhelmed with all the information. I felt like I didn't know how to organize it. So I'm going to show you a resource in the text that will help you organize this information. And I'm going to go to page, I forget what page it is, so I'm just going to keep scanning through because these are all applications of the conditional probability formula, and to my way of thinking, this is a little bit different. And this is the section I want you to read. Look at this problem. Suppose that 100 circuits sent to a manufacturing plant, 5 are defective. Plant manager receiving the circuits randomly selects 2 and tests them. If both circuits work, she will accept the shipment, otherwise the shipment is rejected. What is the probability that the plant manager discovers at least one defective circuit and rejects the shipment? So I want to encourage you to stop the recording at this point to read this read this section of the text. Then when you come back, I'll show you how I've applied the information in the text. So notice that this information, is this thing working? Sure. This information gives us some probability data. That's the part we need. So I'm going to go over to my drawing thingy-mabobber. There's that, and my drawing thing. So I'm going to draw what's called a tree diagram, which you probably saw in the book. And I like to start my tree diagram with a circle and go. So I am going to draw a branch, and this is the first stage of my experiment. I select a defective television. The alternative is a not defective television, or the superscript C is for complement. These are complementary events because they are the only 2 things that can happen in this experiment. When you select a TV, it is either defective or not defective. For any particular TV, that is the case. So we now know that of the 15 TVs we were selecting from here, 3 were defective. And don't get too excited about writing that fraction in simplest form. I'd say just leave it that way. This means that 12 of the 15 TVs are not defective. So imagine this as separate events in time. If you choose a defective TV, you're on this path, and that happens 3 out of 15 times. A not defective TV happens 12 out of 15 times. That's where this probability information comes in. Now, remember, this experiment has 2 stages because we're selecting 2 televisions at random. So if you choose a defective one on the first go, this is absolutely sampling without replacement. We are not putting a TV that we chose here back in, which means there are only 14 TVs to choose from in this scenario. And of course, either the TV is defective or it's not. Now notice you have to look back and see that, oh, well, I chose a defective TV, meaning there are only 2 defective televisions left to choose from. But here, there are still 14 TVs to choose from. And there are only going to be 12 possible choices because remember, we chose a defective one, but here, I don't know why I wrote D, that's C, there are still 12 TVs left to choose from. The probability that we get a not defective TV here is 12 of the 14 remaining TVs that are not defective. Similarly, over here, this branch is a 3 out of 14 chance of choosing a defective TV. Notice that given that we chose a not defective TV, so this is where the conditional probability comes in. I'm going to try to make that less hideous. 3 out of 14 defective, not defective. This is 11 out of 14. So this is the probability. This is a probability model. Wait, no, it's not actually a probability model because I don't know that we've... Actually, I don't know if this is a probability model. I'll get back to you. I think it is. But that just came to me right now, so I'm going to think about that. But now, the probability that both televisions work, there's only one branch here where that happens. And it's this one. And notice that these events are independent because the choice you make here is not dependent on the choice you make here. The probability is, but whether or not I chose a defective TV here is not influenced by the fact that I chose a defective TV here. So the probability that both televisions work is 3/15 times 2/14. Wait, I did that wrong. Hold on a second. The probability that both televisions work. I found the probability that both televisions didn't work. Oops. Sorry. The probability that both televisions work means we want to go down this branch because these are both not defective TVs. 12/15 times 11/14 is to 3 decimal places, 0.629. And I am going to wrap up this video here and see if you can get the second part to work, and I will upload a video where we finish the second part of this question later.